Hi guys. So let's do some C coding today. We're going to do binary search, which we haven't done so far. But we're going to go back and revisit our linear search or algorithm, and we're going to see those both how they behave with each other. We'll call them both into our main function, and then get an output, and then try and understand. Um, the differences between the search. So if you have an unsorted vector and you want to search for a particular element in it, um, I'm pretty sure that um, the linear search takes a longer amount of time. Um, and the time that it takes for the algorithm to complete it is usually denoted by O. That's what big O notation is in general. Uh, when you linearly check, if it's number 9 out of 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, and you're looking for 9. That's 9 operations. You're looking for 4 out of 10. 1, 2, 3, 4. It goes 1, 2, 3. There's 3 operations. So the number of operations changes, and therefore the time of computing changes because you're doing so many operations, right? Um, that's a linear search. It linearly checks element, each item in your vector, in your list, Pythonic list, or dictionary, or whatever your data structure is. Um, Similarly, why is a binary search important is because it's based on a binary tree. Binary tree has a source node called the root, and from the root, usually it's connected to other nodes. There can be an n number of nodes connected to it, which is usually typically it's 2, 3, whatever. And Depending on where the location is of that node, if the node is in the middle and it's connected to two more and it's connected to the root node or whatever, it's more like a central node. But if it's on the edge and it only has one connection down there and it's connected to the secondary level, so at the second level it only has one connection uh, to the next level. It's an edge node. And then the end node is usually called the terminus or terminal node. So that's what it is. It's also called a sink node in graph theory. That's what they call it. Anyways, that's what that is. So far we've covered a few things. We've gone over some basic data types, right? Things that we've covered. Uh, we've looked at data types. We've looked at uh, bubble, sort. We've done linear search. We've done Huffman compression, and now we're looking at binary search, right? So we're gonna look at that. This kind of file. So we're gonna make a new class here. A source file for our code. We're gonna call it binary search. Here we go. Right. Okay. Let's think about this a little bit. What makes this special? Sort. Okay, so we're gonna have to sort. So that's another thing. Like for binary search, it would be a good way to be able to sort the the list, the vector, if you ran a sort command that's inbuilt on it first, and then you went to the middle of it, and then you picked a larger or smaller number. So let's say you're looking for 8. So between 1 and 10, you would pick 5 that you would say is it larger or smaller. And then it's the large side, so we can just pick that side. And we can say between 5 and 10, is it bigger or smaller? If you say bigger, then we're on the right side, right? And then we split in half again. So we say 7, we pick the middle point between 5 and 10, which is 7, and we say, is it bigger or smaller? And you say bigger because it's 8, right? So then you pick 9, which is in the middle. And then you say, hey, is it bigger or smaller? If it's smaller, you already picked 7, you're at 9, so you know it's 8, so you say 8. And that has a limited amount of operations for 8. Instead of having 1, 2, 3, 4, 5, 6, 7 operations, you've had a central 5, and then 7, and then 9. So that's 3 operations, and you got to the number in the 4th operation, right? So 4 as opposed to 7. So that's conceptually what it is: linear versus a binary sort. That's the benefit of using it. It cuts down on the number of operations. So we want to let's go over here to our other files, to Hoffman compression. We need string standard. We need standard here. We're going to take IO stream as well, so that we don't have to print these big statements. Let's put that there. We can do, so there's this, for sort, you use algorithm. So that allows you to sort, right? And then for vector, you want to include a vector as well, because that's the kind of data type, that's storage that we're going to be using, right? So that's pretty much all we're going to need, and the ability to print, right? And the IO stream is for input output, right? So that's for it's very jelly to call this stuff. In Python, they call them arrays too, I guess. Well, dictionaries is more hash maps is under the hood. So dictionaries are lists. It's more what we want to use. It's for the sort call, you know. So if you want to have a vector there, and then you want to be able to run sort on it, so you want to have that, right? And this is I don't need to put. It just eliminates the standard and the 2 colons at both ends. It cleans up the code a little bit, right? So what we want to do is we want to make our first. Let's do linear search first, right? So let's just we can go over here and get search up here. This is how we did linear search, if you remember. And that's how I did it. We looked for 8 and then set position number 6. 1, 2, 3, 4, 5, 6. It's right there, right? So we could take this linear search right there, like that, and we can use that over here, just like that, and then we can call it in our main as well. We can pass the vector, the key we're looking for, just like that, right? How else could we do this, right? Okay. Let's jumble this. So let's go 9, 5, 3, 8, 1, 4. All right. And obviously, if we run it, we're looking for 8, and 8 is in this position right here. It's in position number 4. So that runs right there. And if you go under build, the executable should be created right there. And if it's not there, that's because we didn't go through the manual procedure of building the files. We'll run that. Build it. And we want to execute it. There you go. Right. There you go. Why am I not able to see the binaries? Why was it created here? So it's the bubble sort executable. I think that's because I ran them from here first. Because you can go into CMake build as. Huh. Wonder if I delete it. Make that cd build cd bin. It's not there. Oh yeah, it's not. Obviously it's not there because it needs to be added to the CMake. There we go. All right, so that's how to implement CMake, right? And that's our binary search. What we want to do is we want to tweak the code a little bit over here, right? For our linear search, cost vector, integer, and want to change the vector integer in the key. Let's call this, instead of v, let's call this data. Let's go up here. Let's change this into key. Okay. Into key, we don't need the anti. Like that. Let's remove this logic right here. Okay. And array, we're passing the array in. Here we have a vector. And linear search, what we want to do is we want to just pass in data. So it's called linear search. So there's nothing wrong here. Oh, and we only want to pass in the data and the key. Okay. We don't need any of that. Right? That's it. So that passes it in here. But then the logic, we have to write the for loop for the logic. Right? So we can do that. So this is the structure for loop in the more traditional languages. It's not Pythonic, right? So it's not like for x in range or for I in list or whatever the data type is. You have to you're taking in an integer over here that is the key, right? And you wanna be able to set that up first. And then also the array. You want to deal with the array, right? So first you want to do int I, right? And then you want to give I is less than array size. And that's why we imported that algorithm in line 6, right? So that right there, and then you want to plus plus I. So there's an increment going on, right? You want to do that, and then you want to give another set of curly braces, and you can give enter. So this is the general. So you want to initialize it like that. You want to give that. Give that not a comma. That, right? So that's the structure of a loop, right? So you say, hey, I is equal to this. So whatever the size of this, as long as I is less than the size of the array. So if this is empty, this will obviously fail because the size will give you a 0 value, right? And that 0 is not left. If you do 0 and 0, it becomes false. And if this becomes false, then it won't run, and then it won't loop around with the fresh value if I increment it over here, because I goes I plus plus, right? So you want that, right? And then you say if array square bracket I, that's how you access the array, is equal to the key, right? If it's equal to the key, then return the value, right? So if 8 is found, it's going to do the comparison. It's going to say, oh, hey, only keep looping this thing, for 9, 5, 3, 8. And then when 8 is equal to the key, because the key is 8 being passed in here, then return the value that I is at that point is going to be 8, right? And obviously, if there is no match, you want to return -1, right? Like that. Usually you return 0 to donate that the program is exited with fidelity. Like that, maybe? Yeah, I don't know. That. Is it found a string, maybe? Found that index. So if we do that, if we found an index, right, then we can obviously run the I. We can put out the value of I, right? To string integer value is you just put I in here. Like that. I did. I is not equal to 1. These remaining. Just I don't like the not equals to here. That's what they should be. Like that. So what does this thing do? This will put it out like a linear search. Is not equal to this the value. It's found at index, not found, and line. Okay. This is found at index. There you go. So that's the basic linear search. Keep it as simple as possible, like really concise, right? Now, the binary search, we want to compare whatever is to the right with the left and do a less than equal to operation, right? In a while loop and keep swapping them, right? And if there's a change in it, then we want to end it, right? So that's how we want to do the binary search. At least I'm thinking we want to do that. So we'll do the same thing. We'll have a sorted vector in it, right? With the target key, and we want to get the index. We want to do the same thing like return -1. That's how we want to build it. And we want to pass in the same structure. So this structure and this structure will end up being the same, right? So we can like copy this guy like that and just go binary search, right? And then we want to remove this, right? The for loop right there. We're gonna return -1, right? Like that. So we're gonna have to do a left and a right based on the array size. So we're gonna have to do that. So let's do that first. Let's go end left is equal to, let's assign it to 0, right? Right. Forgot to run this chat of mine. Sorry about that. That guy going right there. Completely forgot about that. Yeah. So this is what I'm going off of for my base understanding of these algorithms, right? It's that. If you look at the images right here for the binary search, right? It just goes half, half, half. So it goes middle, and then the middle of the other one, and then if it finds whether it's high and low. That's the generic idea of this thing, right? And that's what I like discussed earlier as well. Another really good binary search is here in telepath. This gives a very like sober breakdown of how the algorithm works, and it's the pseudocode right there, right? So you have the that's it sets it up in a different way, right? It says that the low hat. It says that the low and high have to be certain values, like less than equal to, and I'm equating them to start them off with. So that's, and it has an awesome flow chart as well that you can see. for binary search, right? It says left is equal to 0, right is equal to length minus 1. And that's exactly what we're doing. Left is equal to 0, and right is equal to, here, let me show it up here really quick. This was binary search, left is equal to 0, right is equal to array 1. Then you code this, left is less than right. If it is, return -1. If yes, then set the mid value to the floor of left and right divided by 2. Then code this array mid target again, and then say yes if it's the mid, if it's a match. If it's not a match, then you go here and then you do the mid target, which is the next mid target again, and then you have a less and no, right? Depending on whether the value is larger or smaller. That's what it is. If it's on the left or on the right, right? So if it's on the left of the mid, then you go +1. If it's right of the mid, you go -1, and then you go back to the floor. And that's the loop. So it's kind of going to end up being like, anytime you see this kind of a loop in a diagram, it's a for loop. But what we're really doing is we're taking this algorithm and we're programming it. So that's the connection between the diagram and the code. So we're gonna go off of that, and I have it up here as well. That I'm peeking at the IntelliPath diagram. Let's keep that up over here because it's really going to help. Let's do array dot size again. And then if you remember, it was -1, right? So you do -1. So that sets that up, right? And then you do your while loop. So while left is less than equal to right, right? Do this. Do int mid is equal to left plus right divided by 2, right? What is it? Divided by 2. So take it from the top down. Left starts at the beginning of the array. Right starts at the end of the array with the -1. Right. Then what we're doing is with the while loop, we're continuing as long as there's a valid range of left less than equal to right. Then we are creating the middle of the index, right? So left plus right, or this can just be left plus right to get the mid, right? Um, but we're avoiding overflow here. So this can also be, otherwise we would have overflow. So to avoid overflow, we uh, otherwise we can directly use left plus right. I can plus right divided by 2, right? So we just want to do that, and that'll be a easier way to do this, right? Um, but since we want to make sure that the code can take all sorts of larger arrays with a lot more data, we don't want to overflow it, right? Um, so that's the one thing. Let me check something. I want a better explanation of this. So avoiding integer overflows in C++. So this is something to read around this, right? Yeah, there's bit allocation. So the moment you use a keyword like this, like int, there's an internal ASCII, an internal, um, it's not a floating point number, it's an integer. It has bit data type ranges, right? So you can do that. So when it goes larger than a particular amount, there's an overflow and the integer won't be able to take it. And I believe for signed integer, we're looking at these values. So there, that's the value. So if I go into my array list over here and I just type in like something like that, that's a lot longer, it's gonna fail. It's going to be integer overflow, and I'll have to specifically change the to be able to change this data type in order for it to. It has to be some other kind of int in here. I think it's called a double vector. Let me see what I can change it to. It's not just like pipe dynamic, like size. It deals with the size and it increases the data type automatically, right? So that's really the problem that you're facing that we're trying to avoid. That's why you have this set of code over here. In this way, right? It tracks it before and the value on the left, to keep it within this particular range of numbers, uh, right? So that's overflow right there, right? So getting back to what we were looking at, right? So we did a left-right initialization. We did a while loop. We did left is less than right. Then we created the mid point, right? And then we ran an if statement. And we said, hey, if the midpoint is equal to the key, then just return the mid, and that's the end of the program right there. It finishes right there. Otherwise, if it's less than the key, go left. Otherwise, it's obviously greater than the key, and then go right and then subtract one, right? And then just keep loop over and over again until you get to this part where there's a match. And when there's a match, just dump it out onto the console. Now the code won't run because we haven't really called that binary search, right? So that's binary search view. Um, so again, so that's where that's assigned integer. Uh, that's where we ran off of. This is the binary search link, right? Uh, okay, we have that over there. Let's call it, and then run it and just deal with this bad boy. So that's for good functioning. You want to return output 0, right? And then for binary search, the binary search takes in two objects, a vector and a key, right? So we have that. Let's go over here. Let's start putting some stuff on the console. Data begin, right? Data dot end, right? We want to do that. That. I'm gonna run on it. I'm gonna run sort on it. Right. So then what is the output? We're taking this thing right here, 40, this, 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 like that. Okay. So with this sort is going to take the beginning and the end and sort it. It's the first thing that we want to do, right? And then we come over here. So it's sorted. Do we want to create an object with it? No, no. But when we have sort, if we pass that in the data that is sorted, it's going to go directly into binary index, into binary search. So, and binary search index. That's an integer. We want to know what position the number that we're searching for is found. So let's go 987 over here. Let's go 987. So we're looking for that position right there. 1, 2, 3, 4, 5, 6, 7, 8. Looking for 8. There might be a repeat, and there's 5 is repeated in there too. So maybe it'll put 9 out. We're gonna find out. So we call the function, right? And we want to pass in 2 variables, data and key. That's it, right? Keeping it quite simple. And then, why? Okay. We're going to go out. We want to take this exact same thing that we did over here. Makes sense now. Now you see what the conflict is happening because we use I here in multiple locations. It's crying out a little bit, right? So we want to call the integer linear do we do? Yeah, index. Or actually, we don't. We have it unique over here. It's binary index. So we can just go here and append that as binary index. We can go here and put that in there as binary index, and then we can go, yeah, that should do it. Why is it binary index is less than equal to 1, founded index, toString binary index, which is the integer, not found. Why? Whining? Why? What? Okay, I'm guessing that at the end of the line I didn't add the semicolon. Right. So that's what it is. So if you write the number of operations, well, if you put the debugger on, you will see that for this exact same vector, when this function runs, the linear search function on line 35 runs, it runs 1, 2, 3, 4, 5, 6, 7, 8 times the for loop. Right, and then when you run this, it's gonna just directly split it in 1, 2, 3. It's gonna sort it, and then split it, and then go left, right, and then split it again, and then go left, right, and then immediately compare and hit this compare and put the output onto our screen. So when it sorted it, it got up to the end. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So at index number 10, which I guess starts to 0, the index starts to 0. Yeah. The index starts 0 because we started the left at 0 instead of 1. If you remember over here. Why is this crying? No, don't worry about that. If you put the debugger on over here, at the for loop inception of the for loop right there, the if statement, and then if you put it over here, the while, right, and then you put it the if statement, you debug it. You can say that, see, they were looking for the key 987 in this vector, and then you can see the for loop run 7 times, right? And let me push it through. So 1, 2, 3, 4, 5, 6, 7. 6, you're in I6, I7, and now we're done into the while loop. So this is completed, and you got it's run 7 times, right? So now over here, it's sorted your array, right? If you go over here, you see the value sorted over here, 88, 55, 49, blah, 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 whatever, right? So the standard vector integer is sorted. And then because it's sorted, even though it's sorted, it's at 987, which is index number 10. So the first thing it's going to go to run one operation here. It's going to run one operation here, right? Between 5 and 10 is 7, 8, 7, or 8. Well, we'll see. And then it's going to run one more operation, 3, 4 operations as opposed to 7, right? And we'll see that one. So 1, 2, 3, 4, done, right? So 4 as opposed to 7, and that's the efficiency of these two. Anyways, thank you so much for joining. I appreciate your time. I hope you guys had fun, and I will see you guys in the next algorithm. Take it easy, and thank you again, and have a nice evening.